So when you're kind of reading through this, they talk a lot about there's some function and that it's continuous on the interval -5 to 5. And then they tell us this one fact about the integral of the function from 0 to 5 is 4. And then they start to ask us questions about other stuff. So when you're looking at that first one, when we're looking at part A, what do you notice? So what'd you notice? What'd you notice, Jordan?
So I noticed that there was the same thing for A, but then +2.
Okay, so it's the same thing that we know information about,
Yeah.
but there's this +2 inside of it.
Yeah.
So if it didn't have that +2, that'd have been great. We would have been able to take care of that, but it does. So I guess we're wondering, how does this change what's there? Like, how does this change our thinking on it? Jordan, go ahead.
I saw the +2 as a vertical shift, and so if you're graphically, if you drew the function and then you shifted it up 2, you know that your function has the area under it is 4, and then since you shifted it up 2, you'd have to take that additional area of the 2 times the same interval, and then you get the total area.
Okay, so we've got this yellow area, and you're saying that whole thing gets shifted up 2,
Yeah.
right? And so then on our purple one, we're going to get that same area just shifted up 2, right? It's all right there.
Yeah.
And you're saying what else?
And then we can just add those together to get the
Add what together?
2 areas.
The yellow and the purple?
Yeah.
Did you notice how there's some overlap? I mean, because we really took this yellow area right here and we moved it up. So it became this purple area that's really right here. So maybe I can't just add the yellow and the purple. Like, what's changed? We have a giant rectangle on the bottom. How big is that giant rectangle, Robert?
2 by how long? So 5.
Yeah, because we're going from 0 to 5, so we know it's a 2 by 5 rectangle. And so we can just take what we knew, which was that yellow area, or the 4 units, and we can then add on that giant rectangle, which is the 2 by 5, and that'll give us our total purple, right? Which is now 14. What questions do you guys have on that method? Looking at it graphically, similarly, I could really take that purple and I could just say, all right, that's the integral of f of x dx from 0 to 5. And then I could say, all right, but I want to add on the integral of from 0 to 5 of 2 dx. Think about it, when we take derivatives, we take them in chunks, right? And really, when we take antiderivatives, we're taking them in chunks. We're looking at each term separately and taking its derivative, or each term separately and taking its integral. And so I can do the same thing here. And if you do that, notice this is where we get our 4 from, right? And then this is where we're getting our, if I took the integral of 2, I'd get 2x on the interval 0 to 5. That's where we're getting that 10 from, that 2 times 5 rectangle. And so that's how we're getting our 14 in total. So using that same idea, look at B. What do you notice is different about B? Emily, what did you notice was different about B? Yeah, that 2 is added on to the x, so it's within the function. So what did that make you think of? So we had this yellow area. We don't know what the function looks like, but it looked like something like that. We can just make it up. And Emily's saying this whole function got shifted to the left by 2 units. So I'm actually going to start back here, and then something like that. Maybe it's not perfect, but we see the idea. So it all shifts by 2 units back. So how does that help us? And what else do you notice? And why? I mean, why is that nice, Owen?
Well, I noticed that the interval you're taking the integral on is also shifted to the left 2 units, so it's the same.
Right. So we were looking for 0 to 5, and now we're looking for -2. That's not a 2 to 3. And so the function got shifted back. Our bounds got shifted back. So what's the answer for B? 4. It's the same exact like area that we were looking at before. It just got moved. No big deal. What questions do you guys have on that one? All right. Moving on. Take a look at C. What the heck does it mean for F to be even, and how are we going to go back to -5?
What would happen if the bounds were shifted?
Go ahead and look at C. Notice now we have to deal with bounds of -5 to 5. I don't know anything about -5 to 0. I only know about 0 to 5. What does it mean for F to be even? Tawny? It's mirrored. So if I just keep going with the same type of looking function that I had there, it's mirrored. Mirrored where? Along that y-axis. So it's actually reflected over that y-axis. So whatever was there, I would actually see over there as well. So really now think about it. If I'm looking for all of this area, what's the answer? 8. I have 2 of what I would have had before. Yeah, Brandon. That's the definition of what an even function means. Even functions are like, think about x squared. X squared has that symmetry across the y-axis. X to the 4th, another even powered function, has that symmetry across the y-axis. Yeah, do you remember that from our little one-day convo where we explored that? This is where it becomes nice again. If we understand even and odd, we can use those properties. If we can recognize when a function is even and odd or what type of function it is, we can change our bounds, and we can do that selectively. Here it's forcing us to do it, but even on other problems, we can do that selectively just to make our job easier. Yeah, so odd it is flipped over the x and y. So if I had, this same looking function, it would have gotten flipped over, wow. You can kind of see it, right? So that's flipped over the y-axis, but then it would have been flipped over the x-axis as well, and so it would have looked, let's see if I can actually visualize this. Right? So we really would have had this for D. Right? We would have had all the pink. So think about the integral from -5 to 5 now. It is 0. That negative area cancels out our positive area. So, and this is the beautiful thing about odd functions. If you ever realize they're odd, you can chop out huge sections of whatever integral you're looking at because you realize that your negative area and positive area balance themselves out. So if I had a problem like this, x cubed dx from -2 to 2, I don't have to do any work integrating that. I don't have to go to x to the 4th over 4 and then plug in my bounds. If this were a problem that I was asked to solve, I'm instantly looking at it and saying 0 because I'm making that connection that x cubed is odd.
So as long as they're lower enough, they're going to take the same absolute value.
Yeah, because it's really that reflection, that double reflection over the y-axis. And this is where we get to be creative, right? We can solve problems creatively. I could solve this by hand. Actually, I could solve this and integrate it and take the bounds and plug them in and evaluate it and all that stuff. And maybe it takes me a minute to do that. Or I make the connection that that's an odd function realize the bounds are really the same right as they are left from 0, and instantly write down the answer. The more we think, the more efficient we can solve these problems. Some AP problems will take, actually they'll be darn near impossible without thinking. If you try the way that they actually are suggesting that you do it almost by the setup, you won't be able to get through it. But if you think and make some connections and look at it differently, then it's like a 10-second problem.